Hi, and welcome to this second video on data structure lower bounds in the self-probe model. And so in this video, we're going to prove the first lower bounds. Particularly, we're focusing on so-called static data structures. And the techniques we'll see for proving lower bounds are using so-called communication complexity. So just a real quick recap first. What are these static data structures? We also talked about it in the previous video, so I'll go really quickly over it. So the goal in a static data structure is to represent some set of input data so that you can answer queries about the data efficiently. An example could be representing a road network of a country, maybe Denmark, which is your data set, and such that given two cities, which is your query, you can compute the distance between them along the shortest path efficiently. Right? So here's the road network and perhaps the distances on all of the edges. And your query now could maybe ask for what is the distance between A and C along the shortest path. This is the shortest path. The distance is 7. So the answer to the query A, C is 7 in this example. Right, so these are static data structures. You get the input once and for all, pre-process it into a data structure so you can answer queries about it. And we also talked about in the previous video, we defined this model that we're going to use for proving lower bounds. And we also motivated this model called the self-probe model. So in this model, right, a static data structure is a collection of memory cells, S of them, where S is the space usage of the data structure. And each of these cells stores W bits. W is assumed to be at least the maximum of log S and log N, so that you have enough bits to store the address of any other cell inside a single cell, and also to store an index of, say, an input object if N is the size of the input. And basically what we're saying is that these bits in the memory cells are encoding the input data set. And which basically means we don't really care about pre-processing or anything in this model, pre-processing time. So basically, we just assume that there's some mapping from all the different inputs, all the different graphs you could have as input to some memory representation. The queries, in a query, we're allowed to probe, which means read up to T memory cells. And once we've read these T memory cells, right, we have to announce the answer to the query based on everything we've seen so far, right? So in some sense, this was meant to reflect that you kind of can remember everything you've seen, that your CPU has enough registers to remember everything. And T here is really the query time, the number of memory cells you have to read to answer a query. And we allow basically that the memory cell that you probe in every step can depend arbitrarily on everything you've seen so far while probing and the query itself. And we also talked about in the previous video that we modeled this by having a depth T decision tree for every single query, right? So go and watch that video if you forgot. Okay, so this is the model we want to prove lower bounds, and it was just a quick recap. So now let's get to some concrete techniques for proving data structure lower bounds. So we wanted to argue in this video here, how can we prove lower bounds for static data structures in this self-probe model? And we're going to see some techniques that are based on communication complexity. Right? So communication complexity is an old, I guess, area or subfield of theoretical computer science. Right? It has a lot of really beautiful techniques, and we're just going to use the simplest ones of them in this video. So while we're presenting all these static lower bounds, I'll also try and present them in what you could say the order of how strong they are. So I want to I want to present every time a stronger lower bound than anything before was proved. And so to compare these lower bounds that we're going to see, I'm going to make a couple of assumptions that makes the comparison a little easier. In particular, I'm going to state the lower bound on the query time, the number of cells you need to probe, in the setting where we assume the space is just linear. Okay, so that's one assumption I'm going to be making when I'm comparing the strength of the lower bounds. I'm also going to focus on data structure problems where the number of different queries you can ask is only polynomial in the input size. So for instance, for the graph problem, right, if you have a graph, there are n nodes in the graph, there are only n squared possible queries, pairs of cities that I can query for, right? So there's a polynomial number of queries. So this is what I'm going to focus on just to make things simpler. And I'm also going to assume then, since we have linear space, S is a linear, number of queries is polynomial. So we're going to assume that this word size, the W, the number of bits in the memory cells, is just some constant factor times log n, right? So it has enough bits to store any address, the address of any memory cell, and also to store a query or an index of an object. Okay. And the first technique that we're going to see is from 1995 by Milterson. And basically the lower bound that we're going to derive from this technique is that the query time has to be at least C. right? So the C up in the exponent on the number of queries, right? So of course, for data structure problems where there's a polynomial number of queries, it's only a constant lower bound. But Mill doesn't really look at problems where you have many, many, many more queries. But also the proof technique itself is kind of the basic, the first step towards more advanced techniques later on. So let's start with this technique, right? So how can we use communication complexity to prove static data structure lower bounds? So the idea is whenever we're looking at communication complexity, we have a communication game between two players that we always call Alice and Bob. And they can talk to each other, they can send bits. And the goal for them is to solve some problem while communicating as little as possible. And when we're trying to prove a lower bound for a data structure problem, the reduction that Milton came up with is such that Bob always receives the input to the data structure problem, the data as his input. So he receives, say, a road network. That's the input to Bob. Alice receives a query to the data structure problem, so a pair of cities. So if it was the Danish road network, maybe she receives the two cities, Aarhus and Copenhagen, and needs to compute the distance between them along the shortest path, right? So the goal really in the communication game is for Alice and Bob to compute the answer to Alice's query on Bob's input, right? And they're supposed to do it while trying to minimize the number of bits they need to send to each other. Okay. And now the reason why static data structures are related to this communication game is that if I have a data structure, I can use it to obtain a protocol, a communication protocol for this communication game. Right. So what could you do? So the way that a data structure gives a protocol is that Bob having the input to the data structure problem could start by constructing the data structure on this input. And now the idea is that Alice, who has the query, she knows what the query algorithm is, the decision tree corresponding to a query. So she'll try to simulate the query algorithm of the data structure on her concrete query input. And of course, right, the way that the data structure works is that it repeatedly, when you have a query, you read or probe different memory cells. And so what you're going to do is just whenever Alice wants to probe a memory cell when in her simulation of the query algorithm, she's just going to ask Bob for the contents of the memory cell. So basically, Alice checks, oh, I need cell number 13. And then Bob, who has built the data structure, knows what the contents of cell number 13 is. So he just sends back, well, number 13 contains the bits 0010. And then Alice can continue the simulation of the query algorithm. She knows now that, oh, but if those were the contents, then I need to probe cell number 5. So I ask Bob for cell number 5. This goes on. And after t many steps, if the query time is t, Alice has finished simulating the query algorithm of the data structure. And then just because the data structure is correct, she knows what the answer to the query is. And she can say the distance is 305 kilometers, right? And so if I have a data structure with a query time of t, then you can see that this communication game has t rounds. In each of the t rounds, Alice asks for a memory cell, like asking for a memory cell, the S of them, right, S possible cells, so that cost log S bits when she's asking Bob. Bob replies with the contents of the cell in every round, right? So that's W bits for T round. So this gives a protocol. Alice sends T log S bits and Bob sends TW bits. So you can see that the efficiency of the protocol depends on the efficiency of the data structure, right? Good. And maybe just to make the reduction completely clear here again, Alice has the query also to Copenhagen, so she knows the data structure has a corresponding decision tree for this query. Bob can build the memory representation of the data structure because he has the input to the data structure. And now Alice can just, to start the simulation, her decision tree tells her to read cell number 13 first. So she's just going to ask Bob for the contents of cell number 13. Bob looks in the memory and sees that what the contents are of cell number 13, and he sends it back. And now Alice can look at her decision tree and she knows which branch to take. She can descend into the relevant child and see that now she needs to probe cell number 5 and so on right until we've finished the simulation and Alice has traced the path from the root all the way down to a leaf in this decision tree, and the leaves of the decision trees store the answers to the queries, right? So she knows now to say 305 kilometers, right? So this is how a little bit more formally that the reduction goes. Okay, so we get this protocol where Alice's communication is T log S and Bob's communication is TW. And now, of course, we would like to derive lower bounds on the trade-off between the time t and the space s. So now we're going to use tools from communication complexity to prove lower bounds. And in particular, the lower bounds that we're going to see are going to be of the form that either Alice is going to send at least A bits, or Bob is going to send at least B bits in any correct protocol for this communication game. And this is perhaps a little different from if you've seen communication complexity before. We usually just lower bound the total number of bits communicated. But here it's actually important because if you think about it, the input to Alice in this example is much, much smaller than the input to Bob in terms of how many bits does it take to describe the input, right? Alice just has the name of two cities. If there are n nodes, this is just 2 log n bits of input, whereas Bob has a whole graph on n nodes and all the edges between some subset of the nodes. So his input takes like the m edges, it takes something like order m log n bits, right? So his input is exponentially larger than Alice's. So it's important here that we prove so-called asymmetric communication lower bound, saying that either Alice sends A bits or Bob sends B bits. So this is what we'll aim for. Okay. And if we could prove such a lower bound, well, then we can just plug in and see, we had this communication protocol, right? So we know now that either T log S has to be at least A or TW has to be at least B. We can solve for T in both of these equations. And this gives us a final lower bound on the query time saying that T has to be at least the minimum of A divided by log S or B divided by W, right? That's the lower bound on the query time, the number of probes, based on the space usage S here, the number of bits W. And of course, then we have to derive this lower bound on A and B. So let's try and do so. So this is really what we want to do using tools from communication complexity to try and prove such lower bounds. And we're going to do it, but we're not going to do it for this problem of finding the shortest path in a graph. Basically because, of course, one can do so, but it's a little bit of a difficult problem to prove a communication lower bound for. So we're going to look at another data structure problem that basically allows for the simplest possible proof you can imagine, just to illustrate the techniques as well as possible. Right. So what is this problem that we're going to work with? The problem that we're going to work with is the polynomial evaluation problem. Okay, so what is this problem? So the input in this data structure problem is a degree n-1 polynomial p with coefficients over a finite field. And we're going to work with the finite field fp, so modulo a particular prime. And we're going to say that this prime is, well, within a constant factor of n squared, right? So it's a little bit larger than the degree of the polynomial, the number of elements of the field. Okay, so could have been any polynomial factor larger, the lower bounds will still go through, but we're just going to say the prime is around n squared. Okay, so that's the input, it's just a polynomial. A query to this data structure problem is just an element in the finite field, an x in fp, so a number between 0 and p minus 1. And the goal is, or the answer to the query is p of x. This is what the data structure has to compute, right? So just to have a small example, right? Let's say that the prime is 7 and n is 3. So then we get a degree n-1, so a degree 2 polynomial as input. Could look like this. So the coefficients are over the finite field f7. So that's numbers. So it's basically we're working modulo 7. So these are numbers from 0 to 6. So it could look something like this, the polynomial. And if we get a query where x is 4, we have to evaluate this polynomial over the finite field f7. So that just means we have to evaluate it mod 7. So we can basically insert 4 here. The number we have to compute is 3 times, well, 16 plus 4 here for the x plus 5 mod 7. So the answer to this query is 1. Right. So this is the data structure problem we're going to look at. Maybe it's not as clean a data structure problem as the distances and graphs, but it's much, much easier to prove lower bounds for this problem. And we're going to think about this problem in the cell probe model with a word size w of theta log n bits, so constant factor times log n. Right, again, this means that you can store any field element in a memory cell. You can store any address of any other memory cell if the space is at least a polynomial in n, and so on. Okay. So this is the problem. And the property that we're going to be exploiting of this data structure from the property that we'll be using in our proofs is that, well, if I have any degree n minus 1 polynomial over fp, if I tell you n points on the polynomial, n unique points on the polynomial, then the polynomial is uniquely determined. Basically, I can do interpolation and recover the polynomial from any n distinct points in the polynomial. This is the same property as over the real numbers. So this is the key property of polynomial relation that makes the lower bounds proofs very easy. Okay. Basically, well, since knowing n minus 1 points, n points on a degree n minus 1 polynomial reveals the polynomial, the property really in terms of data structures is that, well, if I can somehow determine the answer to a query x, then that answer tells me a point on the polynomial, namely x comma p of x. So somehow the thing that we're going to try and do is to try and answer a whole bunch of queries, in particular n many queries. So we have n points on the polynomial, and then we can somehow recover the polynomial. This is basically the property that we'll be trying to exploit. Right. So back to this communication game between Alice and Bob. Now, if we want to prove a lower bound for polynomial evaluation, then Alice receives a query, which is an element of the finite field F7 or Fp in general. So maybe Alice receives x equals 5. Bob receives a polynomial as input, degree n minus 1 polynomial with coefficients over Fp. And we're assuming that this prime is around n squared large. Okay. So using tools from communication complexity, we want to prove that either Alice sends some number of bits or Bob sends some number of bits. And the concrete lower bound we're aiming for is that either Alice is going to send at least log p divided by 4 bits, or Bob is going to send n log p bits. If you think about it, how many bits does it take to even describe Alice's input? It's an element of a finite field with p elements in it. So it takes log p bits to just describe Alice's input. So this is a pretty large communication lower bound compared to the size of her input. She either has to send log p over 4 bits. And Bob's input, right, if a polynomial of degree n minus 1 has n coefficients. Each coefficient is an element of a finite field of size p. So basically this says that Bob has to send the entire input. And so we want to prove that one of those two things must be the case. And indeed, if we can prove this, then we get this conclusion that either t log s is at least log p over 4, or tw is n log p. So basically, if we solve for t, we get either t is log n over log s, or t is n log p over w. We said our log p here, since p is around n squared, this is just log n. W, the number of bits in the cell, was also log n, so this just cancels out and becomes n. So basically the lower bound is either t is log n over log s, or t is at least linear. Right? So the minimum of the two lower bounds is, of course, the first one. So we get a lower bound that t has to be at least log n over log s. Right. So let's try and prove this. So we're going to use this standard technique in communication complexity called a rectangle argument. So let's assume that, so basically the way we're going to prove it, the lower bound statement was that either Alice sends at least log p over 4 bit, or Bob sends at least n log p bits. The way we're going to prove it is we're going to assume, well, let's assume that Alice does not send log p over 4 bits. Then we want to prove a lower bound on Bob's communication. We want to show that this number of bits b that Bob sends has to be large. The way we're going to do it is we're going to look at this matrix where there's a row for each of the possible queries of Alice. Right? So for every x in the field, there's a row. There's a column for each of the possible polynomials that Bob could have as input. There's p to the n different possible inputs. And in each of the entries of this matrix, we just store the answer to the query x on the polynomial p. Okay. Now, if I have a communication protocol, a standard technique in communication complexity is to show that this protocol implies the existence of a so-called rectangle or combinatorial rectangle. I'll try to show you what it is. So what is the property of this rectangle that we're going to zoom in on? Well, the rectangle has a number of rows that is at least, well, the total number of rows of Alice divided by 2 to the number of bits that she's communicating, 2 to the log p over 4. If you look at this number, it's p to the 3/4. P was around n squared, so there's a lot more than n rows in this rectangle. And the number of columns is the number of inputs of Bob divided by 2 to the number of bits that he is sending. And inside this rectangle that we're going to zoom in on, I'm going to show it in just a second, the special property is that the answer to every query of Alice is fixed inside the rectangle. So it's the same answer to all of these columns of Bob. So let me try and visualize this. So the reason why this must be the case is that you could follow the communication protocol. If I have a correct protocol for this communication game, I can try and follow the protocol. And always, whenever one of the players is speaking, sending a bit, I'm going to zoom in on the most likely message. So what does it mean? Let's say that in any protocol, Alice starts by sending a bit. There are two choices for the bit, and you can look at which of the inputs causes Alice to send a 0 and which of the input causes Alice to send a 1 in her first message. So maybe it looks like this. And now we're going to say, well, the most rows where she sends a 1, so let us restrict ourselves to all the inputs where Alice starts by sending a 1. Maybe the next person to speak in a protocol is Bob, and he sends a message on every single input again. In some of them he says 0, and some of them he says 1. I guess every column was supposed to have a color here, so a little mess up on the animation. But in every single column that corresponds to an input of Bob, there's some message that he sends. And let's zoom in on the most likely message. So let's say these are the columns where Bob starts by sending a 0. Okay. So you're kind of restricting ourselves to some subset of Bob's inputs. So now we have so we have subset of the rows, a subset of the columns, and this is what we call a rectangle. This corresponding to a subset of rows, subset of columns. Let's say that now we've done this, we repeatedly zoom in on the most likely message until there's no more communication in the communication protocol. Then we know, because once the protocol is done, Alice knows the answer to her query without any more communication. Well, this means that it must be the case that inside this rectangle, the answer to every query is fixed, right? If she looks at her query, she must know what the answer is. It means that it must look something like this, like all sixes, the answer is all the same, the answer is all the same, the answer is all the same. And so this has to exist because the protocol is correct, so she must know the answer to the query here at the end. Now, maybe if you've seen communication complexity before, there's a subtle detail here that's actually important, and that is that it's Alice that knows the answer at the end of the protocol. And in typical communication complexity lower bound, you assume that both players know the answer to the query, or to the query on the input. And this is because, I guess, in many cases when you prove communication lower bounds in communication complexity, you look at problems where the output is just a single bit, which means that, oh, well, you can always come from this situation here where Alice knows the answer to a situation where both of them know the answer. Because when Alice knows the answer, if it's just a single bit, she can just send it to Bob, and then they both know the answer. And basically we zoom in on a rectangle where everything is the same inside this rectangle, that it's all ones or all zeros. So if both player knows the answer, it has to be the case that the rectangle is so-called a monochromatic rectangle. It's either all zeros or all ones, or it's all the same, at least. That's what we mean by monochromatic. The reason why we're not requiring this in our reduction, why it's actually important that only Alice knows the answer, is that for a problem like polynomial evaluation, the answer is actually log p bits. And so if Alice has to send these bits to Bob, she's just telling Bob the answer is as many bits as just sending her entire input to begin with. And this really breaks any lower bound we could hope to prove, right? So it's really because Alice's input is so small that we cannot even afford to tell Bob what the answer is. So basically, when we want to prove a lower bound here, we can only assume that it's Alice that knows the answer to the query. That's also sufficient, it turns out. Alice knowing the answer, it means that every row is monochromatic or fixed inside this rectangle that we get. Okay. So let's go back and try to prove this communication lower bound that we claimed up here. The lower bound says that, well, basically what we want to argue is that if Alice sends less than log p over 4 bits, then Bob has to send b bits for a large b. Zooming in, again, as we did before, just following the protocol, always fixing the most likely message, we get that the number of rows that are left in this rectangle is at least p divided by 2 to the log p over 4, which is p to the 3/4, which is more than n rows. So there's at least n rows left in this rectangle. The number of columns is p to the n divided by 2 to the b. And the answer to every query is fixed inside this rectangle. Now we want to argue that b has to be large. But why is this the case, right? But here we're using this crucial property of polynomials, that any two polynomials can share no more than n-1 points, right? It's unique. Any polynomial is uniquely determined from n points on the polynomial. Okay. But if we look at this rectangle here, right, the number of rows in the rectangle was way more than n. Right? So the number of queries is way more than n. But any polynomial that is left in the rectangle, they all agree in these rows that correspond to the rectangle, right? So all these four polynomials that are shaded in blue here, they all agree on all these x's in the rectangle. So they agree on way more than n rows or n points. But by this property here, it means that there can only be one polynomial left in this rectangle, right? Because otherwise you have two distinct polynomials that agree in more than n-1 points. So if there's only one column left, well, the number of columns is p to the n divided by 2 to the b. So we conclude that 2 to the b has to be at least p to the n, right? So 2 to the b is at least p to the n. So b is at least well, greater than or equal to n log p here. So this gives us a lower bound that if Alice sends less than log p over 4 bits, then Bob has to send at least n log p bits. So basically, so this is the lower bound that we actually derived, right? We assume that if Alice sends less than this number of bits, then Bob has to send at least this many bits. It means that one of these two have to be the case. We insert this with the communication that we got from the data structure protocol. So we get that either T log S is at least log P over 4, or TW is at least N log P. And if we solve these two, the lower bound that we get, the weakest of the two lower bounds, is that T is at least log N over log S. Right. So this was Middleton's technique to turn it into a communication game. And let me just say a few words about limitations of this technique. So what are the strongest lower bounds we could ever hope to prove using Middleton's technique? And so his technique is really doing this communication game and trying to prove that either Alice sends at least A bits or Bob sends at least B bits, and then get a lower bound that T is at least the minimum of A over log S and B over W. So I guess the reason why the limitations come from basically there's a trivial protocol, right? There's a trivial protocol where Alice sends her query to Bob, and Bob looks at his input, and Bob can then compute the answer and tells it to Alice. Right, so the number of bits that Alice is sending in this protocol is really, she just sends her input, right, which is log p bits, which is like 2 log n in this case, if the number of if the prime is around n squared. So Alice sends her input to Bob. And what this means is that we can never really hope to prove that Alice has to send more than log p bits or 2 log n bits, right? So this A up here, the highest we can ever hope to prove is that Alice has to send her entire input, right? So that we'll never get an A that's higher than, say, 2 log n in this case. Which means, well, since the low bound we get is T is at least the minimum of A over log S and B over W, it doesn't even matter what B is. We'll never be able to prove anything higher than T is at least, well, 2 log N over log S. Okay. Now, the space usage of any data structure for storing a degree n-1 polynomial has to be at least linear, right? So the number of memory cells has to be at least n. So this log S is at least log n. So the lower bound is never higher than 2. Okay, so this is a little disappointing. And in general, if the number of queries to the data structure problem was n to the c, we can never hope to prove that Alice has to send more bits than what it takes to describe her query, which is c log n bits. So it will never be more than c log n divided by log s, which is just t is at least c, since the space usage is at least linear. So this is why this caps this technique at proving lower bounds of around basically what we managed to prove for this polynomial evaluation problem. Right, so this was Middleton's technique, unfortunately only peaking at constant lower bounds in this special setup where there's only a polynomial number of queries. What we'll see next is a very nice result by Mihai Petrascu and Mikkel Torup from 2006, where they managed to prove lower bounds for the setup of space and number of queries. The first, I guess, non-constant lower bounds of log n over log n. And these lower bounds, this lower bound is based on this reduction from communication complexity again. Right, so let's look at their reduction here. So they're basically going to do a more elegant or more refined reduction. They're still going to do a communication game between Alice and Bob. Bob still receives the input to the data structure problem as his input, so a polynomial in this case. And instead of receiving one query, we're going to give Alice multiple queries, right? That's also, it seemed to be the problem before, right, in the previous reduction, that there's this simple protocol where Alice just sends a single query to Bob and then we're done. So what we're going to try and do is to give Alice more input. So we're going to give Alice K field elements instead. And then the goal for them is that Alice should be able to compute the answer to all her queries while minimizing communication, right? So she, at the end of the protocol, she must know the answer to all three queries, in this case, all K queries on Bob's single input. Remember, so it's the important part is it's the same polynomial they're evaluating it on. Okay. So basically we're still going to say, well, if I have a good data structure, I'm going to get a good protocol for this communication game. And it's going to go basically the same way as before. Bob starts by building the data structure on his input. Alice now is going to simulate the query algorithm still on all her K queries, but the trick is she's not going to do it one by one. She's going to simulate the query algorithm in parallel in some sense. So what does this mean? It means that, well, she's going to simulate the first step of the query algorithm on all her K queries at the same time. Then she knows a bunch of cells that each of them wants to read a particular cell, and she's going to ask Bob for all those cells in parallel. Okay, so this means she's going to say, I need the cells number 13, 15, and 24. And then Bob is going to say, well, they're storing the bits 0010, 1001, 1111. And then they're going to continue like this, simulate the whole protocol. And then Alice, of course, by correctness of the data structure, will know the answer to all the queries. Now, what's the trick here? Why are we doing this in parallel? What are we gaining? So the real trick here in this reduction is that it is actually cheaper for Alice to ask for K cells at the same time compared to asking for K cells one at a time. Why is this? Well, basically because if she wants to ask for K cells in a data structure that has S cells, there's only S choose K many choices for what those cells could be. She needs log S choose K bits to specify the set of cells that she wants. And if you look at standard approximations of the binomial coefficient, you'll get that this is about K times log S over K. The trick here is that per cell, it's only log S over K bits instead of log S bits, that if we specified them one at a time. So it's basically because she can kind of ask for all of them at simultaneously, she'll get a saving per cell that she needs. And she can specify them in a cheaper way. So which means that after these T rounds of the protocol, the communication from Alice will, for each of the T rounds, she sends K log S over K bits. Bob, in each of the T rounds, replies with the contents of K cells, so that's KTW bits. So now we have a protocol again from a data structure. So now we just need to do the exact same thing as before. Now we can use tools from communication complexity to prove that either Alice has to send A bits or Bob has to send B bits. Of course, for this slightly harder communication game where Alice has K queries and not one. And if we can do this, then we get exactly these trade-offs from the reduction that either the query time has to be at least the minimum of A divided by K log S over K, or B divided by KW. Okay, so let's try to prove a low bound. And we're still going to do this rectangle argument. The only difference is that each of the rows of this matrix corresponds to a set of K queries that Alice could have, right? Instead of a single query. And we're going to assume now that Alice sends less than K log P over 4 bits. And we want to prove that then Bob has to send B bits for some large B. So let's try and see. So we can do the same trick. Whenever one of the players sends a bit, we're going to zoom in on the most likely message, the most likely bit that could be sent. If we do this, then at the end of the day, we're going to end up with a rectangle again, where, well, what is the number of rows? The total number of rows in this matrix is P choose K. That's the number of sets of queries that Alice could receive as input. So it's P choose K divided by 2 to the K log P over 4. And the number of columns is P to the N divided by 2 to the B. Okay, now we want to prove something for this. So let's and the property that we have is, of course, Alice can answer all her queries inside this rectangle. Like, so meaning that the answer to every tuple of k queries is completely fixed. Okay. So let's have a look at these numbers. In particular, so Alice can answer a whole lot of sets of k queries, right? But these are all sets of queries. So now we could ask ourselves, how many distinct individual queries can she actually answer inside this rectangle, right? Because each of the sets, they may overlap, right? So you might answer the same query in multiple sets. So we're asking how many distinct queries can Alice answer inside this rectangle? And we'd like to show that this is a large number of distinct queries. So again, each of the rows in the rectangle corresponds to a set of k queries. And these sets are distinct sets, but they can overlap, right? But so what we're going to look at is, let's say, okay, in the rectangle, there's all these sets of queries. Let's look at the union of all these sets. Actually, let's call the union U. That's basically the full set of all the queries that can be answered by Alice in this rectangle. And let's say X is the size of U. We want to prove that this X is large. Okay. So how large is this X? Well, the key property is that, well, all of the rows that Alice can answer corresponds to distinct sets. And all of these sets of k elements are contained in the union, which means, well, that X choose k, this is the total number of sets distinct sets of k elements I can even construct from the union, has to be at least the number of rows that we have left, right? So X choose k has to be at least P choose k divided by 2 to the k log P over 4. Okay. So let's have a look at this. Now we're going to, so let's try to see what does this imply. We want to lower bound X from this. And here we're just going to use a standard approximation again of the binomial coefficient, saying that n choose k is, well, at least n over k to the k, and at most en over k to the k. We're going to use this inequality on x choose k and p choose k, which means that we conclude that ex over k to the k is at least p over k to the k divided by 2 to the k log p over 4. Now, what we're going to do is we're going to take the kth root on both sides, so all the k's and the exponents just disappear, and then it's a nice simple inequality where we can solve for x. We can multiply with k on both sides; they go away, and basically, if we do this, then we get that x is at least p divided by e times 2 to the log p over 4. This looks very nice, right? Because 2 to the log p over 4, that's p to the 1/4. So this whole thing solves to p to the 3/4 over e, which means we have this very nice property that we also had before, right? That the number of distinct queries that Alice can actually answer in here, the number of distinct points on the polynomial that she can determine, is at least n, right? It's more than n. Okay. So since Alice can answer more than n queries, we had this really nice property before of polynomials that any two distinct polynomials can share at most n minus 1 points on the polynomial, which means that there can only be one column left, right? There's only one polynomial left in this rectangle. So this 2 to the b here has to be at least n log p. So basically what we did was we said that, oh, let's assume that Alice sends a few bits at less than k log p over 4. Then the total number of queries she can answer, the union of all the query sets, is bigger than n. Therefore, Bob has to send the whole polynomial. B has to be at least n log p, right? So this is the lower bound, right? Either Alice sends k log b over 4 bits or Bob sends n log p bits. Good. So this is what we showed, right? We showed that for any k you can choose in this communication game, either Alice sends k log b over 4 bits or Bob sends n log p bits. Now, in the protocol that we got from communication complexity, from taking the data structure and simulating it, we got a protocol where Alice sends tk log s over k bits, and Bob sends tk w bits. And now we want to derive a lower bound from this. Okay. The nice observation is that, well, this reduction, it worked for any choice of k. So we can choose k when we want to prove a lower bound. We can choose a k. So what k would we like? Well, if we look at Alice's communication here, right, you can basically see that, well, the lower bound, this grows with a k, and her communication grows with a k. So these two kind of cancel each other out. So the only k that's then left is the log of s over k. So the amount of bits that Alice has to send decreases if we ignore the k factor here, it decreases with k. So in some sense, we would like to choose as high a k as possible if we're looking at Alice's part of the communication. Now, of course, we don't want to choose it too high because then Bob's part of the communication breaks in some sense. So what we want to do is we basically choose k so large that Bob's communication just doesn't exactly hit this lower bound here. So what we're going to do is we're going to fix our k to be n log p over 2tw. Why is this? Well, because if we insert this value for k in Bob's communication, then Bob is sending a total number of bits of n log p divided by 2. Right, so this means that Bob is not sending n log p bits. Right, Bob is not sending n log p bits in this protocol, which means that it must be the case that Alice's part of the communication is at least is big enough, right? That Alice's tk log s over k bits is at least k log p over 4. Right, so we really choose k as large as we can without violating Bob's part of the communication lower bound. So Alice has to send k log p over 4 bits. But she did send tk log s over k bits. So tk log s over k is at least k log p over 4. We cancel the k's on both sides, move the log s over k to the other side, and we get a lower bound that t is at least log p over log s over k. Finally, we can insert the choice of k into this s over k, and we get t is at least log p divided by log of stw over n log p. Right? So this looks like a really complicated expression, but if we actually stare at it a little bit, it's actually quite nice. So let's try and look at it. What does it mean? The lower bound we get by setting the k right is that the query time has to be at least log p over log of stw over n log p. Right. What is this? At least if we stare at these terms inside, SW over n log p. Well, SW is the total number of bits in the data structure, right? There's S cells of W bits. N log p is the number of bits described that is needed to store a polynomial, right? Because that's the number of bits to describe the input. So this number is really the space overhead over linear space, like the amount of extra space you're storing compared to linear, right? So the lower bound is real. So this term is a really nice. It's a space overhead over linear that's inside of this log, and there's also the t, right? Also, if the word size was assumed to be log n, log p is also log n in our setting of parameters. The w and the log p cancel out, so then it simplifies to t being at least log n over log st over n, right? So s over n is the space overhead again. T is the query time. If the space uses is linear, this is what we're comparing in our comparison of the largest lower bounds that have been proved. We get that t is at least log n over log t. This also, if you rearrange things, it implies that t is omega log n over log n. So this is the lower bound that I claimed, right? Maybe there's a small technical remark if you're using this technique was that, well, we said we can always choose k to be whatever number we had before, but of course, k can never, the number of queries that we give to Alice can never be less than 1. And we chose k to be n log p over 2tw. So this number has to be less than 1. And if you solve for, if you say that this is less than 1, you get a bound on t, right? So either the final lower bound is either the one that we just derived before, or that t is at least n log p over 2w. Because you just move t to the other side, and it's just n log p over 2w. So the lower bound is kind of like the minimum of these two lower bounds. But this lower bound down here, again, log p and 2w in our case cancel out. So this is like t is at least linear. Right. So either t is at least, let me go back, either t is at least linear, or n log p over 2w, or t is at least this log p over log stw over n log p. When does this second branch ever matter? Well, In the proof so far, we didn't actually use that p was n squared. It was just at least n squared. If p is something that's not just a polynomial in n, but maybe much, much larger, maybe it's exponentially large in n, then sometimes the second lower bound here kicks in. Okay, but in general, we get these lower bounds. This is most often the case that this is the part of the lower bound that really matters. Okay. And let us also, as with the other technique, let us just check what are the limitations of this reduction. What are the highest lower bounds that we could hope to prove, right? So in the reduction, right, we always get this fact that Alice sends kt log s over k bits and Bob sends ktw bits. We can always try to prove a communication lower bound that either Alice is sending a bits or Bob is sending b bits, meaning that we always get these lower bounds that t is the minimum of two terms. Right? So this is the same as before. So what are the limitations, right? We always have these trivial protocols where one player sends the entire input to the other, and then you can solve the communication game, right? We can never hope to prove that B is larger than n log P or A is larger than K log P. So the trivial protocol, right, there's always a protocol where Bob sends n log P bits. So we can never hope to prove any higher lower bound than this on Bob's communication. We can never hope to prove that Alice is supposed to send more than K log P bits. Okay. If we stare at these two things, what we want to do is, in general, as we saw before, right, the higher we chose K, the better lower bound we got. And basically the amount of communication from Bob, we basically want it to be less than him sending his entire input. So we cannot really choose our K larger than such that Bob is sending his entire input, right? So Bob is sending KTW bits and his entire input is n log P bits. So we can never set K larger than basically n log P over TW. If W, the word size, is about the same as log P, they cancel out, and basically meaning that we can never hope to set K larger than N over T. That's the best we can hope for. If this is the K we choose, then the lower bound we get from Alice's communication is not too high, right? So because we can never hope to prove that Alice has to send more than K log P bits, so if we insert this for A, then we get K log P divided by K log S over K. The two Ks cancel out. So we get like, we can never hope to prove anything higher than log P over log ST over N. So this is really the peak of the lower bound technique. So if the space is at least linear, it is always at least linear, then this lower bound is never more than T is at least log P over log T. And this basically gives T's log P over log P. For polynomial many queries, it's the lower bound we got, log n over log n. Right? So this is the best we can hope for from this technique. Right? We basically achieve the maximum lower bound possible from this communication reduction. Right? So this is the state of the art based on techniques that are using communication complexity. A simple reduction gave lower bounds when the space is linear, the number of queries is polynomial, the lower bound is a constant by the first reduction, and the reduction by Petrasco and Torup, we can get lower bounds of log n over log n. So this concludes the communication complexity-based techniques, and then we'll proceed in the next video to talk about another technique for proving static lower bounds.